Okay. Last time we were talking about probability of error calculations for two-dimensional signal space. And we came up with the following. So basically what we did was we said a two-dimensional signal space, we have two match filters. The noise-free filter outputs are just the coordinates of the signals in signal space, and we had a formula by which we could calculate the probability of error given that a particular element was sent, assuming that the Voronoi region was rectangular. So in particular, we calculated probability of error in this scenario, where each signal point excuse me. Each signal point is located sort of at the unit coordinates of the two-dimensional signal space. Like so. So we said, what do? You select thresholds. Thresholds are now boundaries. We select them halfway between each signal point and each other signal point. So the region in which we decide this one, let's call this 0. Halfway between these two signal points, so everything to the right of that line. Halfway between these two signal points, everything above that line. And halfway between those two signal points, everything up here. And the union of those regions is the Voronoi region for S0. And that's this. Okay, let's look at a bigger example. So we said the probability of error given that an I was sent. So assuming we have a rectangular Voronoi region with X min, X max, Y min, Y max, like so. We said the probability of error given that an I was sent, this is SI, signal space, is equal to 1 minus the probability of being correct, given that an I was sent. And we said that this is equal to 1 minus the probability that, well, what it really is it's 1 minus the probability that the X coordinate is within that range, and, excuse me, it's the probability of being correct is the probability that the X coordinate is between X min and X max, and the Y coordinate is between Y min and Y max. And we said those events are independent. So the probability that, remember phi X was my filter output in the X direction. So that's X min less than X, phi X less than X max, given I was sent, times the probability that Y min less than or equal to phi Y less than or equal to Y max, given that I was sent. And we also said that these can be given by RC. So probability of X min less than or equal to phi X less than or equal to X max, given that an I was sent, this was 1 minus 1/2 RC. So this coordinate SI is alpha I, beta I. So the X coordinate is alpha I, the Y coordinate is beta I. So this 1/2 RC alpha I minus X min divided by root ds plus 1/2 RC C x max minus alpha I divided by root n through TS. So basically, if I get rid of this bracket here, 1 minus this minus this. And similarly for y, all I do here is I replace y min, y max, and the y coordinate beta I, beta I. So let's consider a bigger example. What I'm going to do is I'm going to do an 8-ary. And what I do with the 8-ary is I'm going to do 4-ary in the x dimension and binary in the y dimension. So there's, when you draw these out like this, this is usually called a constellation. When you plot the points in signal space, because they all look kind of like an arrangement of stars, I guess, we call it a constellation. So let's put the y dimension, on the y dimension, I'm going to have this as +1 and -1. And in the x dimension, I'm going to put these at -3, -1, +1, +3. So for instance, this point is at x equals +3, y equals +1. And remember the physical meaning of this. So when I specify my signal space, I specify my basis vector. So I have Sx and Sy. So the physical meaning of this signal is that this is a vector S, which is equal to alpha I Sx plus beta I Sy. In other words, I take this vector, multiply it by +3. So in other words, S0 would be 3Sx plus Sy. And that's the way I'd be able to get the exact value of that signal. Okay. Let me redraw that over here where I have a little more room. Now the task is to find the Voronoi regions. So the Voronoi regions, remember our procedure for finding the probability variant binary. At this point, we would start talking, we know the signal means, we know the noise-free filter outputs. We also know how to calculate the variance, we covered that last time. So at this point, we'd start talking about the threshold, but in two-dimensional signal space, we don't have a threshold anymore, we have Voronoi regions. So, for instance, for this one, for this guy right here, what would the Voronoi region be? Well, let's look at his neighbors. One here, one here, one here. We can also look at the other ones, but they will be included in, we can, just by looking at this, it's clear that the Voronoi region will be selected based on these 3 points. Because if something is closer to here than to here, then it will also be closer to here than to here, and similarly for these guys. So, go halfway between these two, and I get that line. If I go halfway between these two, I get this line. If I go halfway between those two, I get this line. So here's the Voronoi region. If I go halfway between these two, just to follow up on what I just said, then I get a line here, and I take everything to the right of that line. So everything to the right of this line is closer to S0, or closer to this point than this point.